Eric Archer here from TI, and today we're going to do a virtual lab to determine if water is clean. And so what does that even mean, clean water? How do we know if the water is actually clean or dirty? Well, there are government standards to determine the cleanliness of the water, and there are strict standards to determine if your drinking water is clean. So this is really important. We want to make sure that when we make a glass of water and we're drinking it, that there are no chemicals or harmful things that can affect us. But the standards for drinking water are actually different than the standards for bodies of water, aquatic ecosystems, if you will. And so today we're going to look at water samples from some virtual aquatic ecosystems to determine if that water is clean or not. And so knowing how environmental factors can affect water quality kind of helps us predict sources of pollutants in the watershed. So if we take water from different parts of a river, and upstream samples are pretty clean, but then downstream we find a sample where it's very dirty, then we can kind of backtrack from there and find out if there's somebody dumping something in the water, or there's a factory or something like that that probably needs to be looked into. So that's what we're going to do today. To follow along, you can either just watch this video and take notes, or you can download the TI-Nspire CX Premium software, which is found at www.education.ti.com, and download the file titled Clean Water, which is found at www.scienceinspired.com. Let's get started. Okay, the first thing we need to do is just kind of go through some of the variables that we're going to monitor in this virtual lab, this virtual experiment, looking at how clean the water is at various samples. One of those variables is dissolved oxygen, so DO for short. And that's oxygen that's dissolved in the water. So aquatic organisms require oxygen to live, just like you and me. We have to breathe oxygen. The fish in an aquatic ecosystem, they also have to breathe oxygen. They get it through their gills, and they get it from dissolved oxygen that's in the water. So moving bodies of water like rivers and streams, they have high dissolved oxygen because it's mixed in from the atmosphere. More still bodies of water like a lake or a pond, a little bit less. They get the DO from wind blowing across the surface of the water, mixing it up a little bit. And all bodies of water can get oxygen from aquatic plants and algae that produce oxygen through photosynthesis. So DO is very important for the quality of an aquatic ecosystem. All right, next is temperature. And so temperature is important because the higher the temperature of an aquatic ecosystem, the lower the amount of dissolved oxygen. So those things are inversely proportional to one another. So warmer water has less DO, dissolved oxygen dissolved in it. And the way a body of water can kind of warm up is based on air temp, runoff from surrounding environment, turbidity, which is how much stuff is in the water, like dirt or chemicals, the depth of the water. So the deeper you go, typically it's a little cooler. And of course sunlight. So sunlight can heat up the surface of the water very quickly. And then things like shallow creeks and streams can heat up faster than, say, deeper bodies of water, just because they're more shallow. And then the warmer the water, like we said, the less DO there is. And so this is sort of the key factor here. So the warmer the water, we know that there's going to be less dissolved oxygen. We know from the previous slide that DO is an important variable for aquatic organisms. Okay, pH is how acidic or how basic a solution is. And most fish, they'll tolerate pH values that are anywhere between 5 to 9. And the pH scale ranges, it goes from 0 to 14. And most rivers, lakes, and streams in the U.S. fall within the 5 to 9 range, though acid rain can lower the pH of these bodies of water. So you can get pretty acidic bodies of water, and the fish and plants can't survive that. All right, another variable might be new to you is turbidity. Turbidity. And that's a measure of how clear the water is. It's an indicator of suspended sediments that are in the water. So if you took a handful of mud or dirt and you threw it in a glass of water and you mixed it all up, it'll be very cloudy. and so it'll have a high turbidity versus a clear glass of water, nothing in it. It'll have a very low turbidity, maybe zero. And so that's what turbidity is. And turbidity can tell us things like how much erosion there is from the surrounding environment. Runoff, like let's say a big rainstorm comes and the water runs across the land, down the watershed into the body of water. Well, along the way, that water is going to pick up things like silt and dirt, and then chemicals from urban and agricultural areas like fertilizer, which increases the turbidity of the water. So turbidity of surface water is usually between 1 NTU and 50 NTUs. So an NTU is just a unit. If you're really interested, NTU stands for nephelometric turbidity units, and nephelometric just refers to sort of the instrumentation that's used to watch or to look at the turbidity, how cloudy the water is. Basically, it shines a beam of light through one part of the sensor, and then lets water in between the beam that's broadcast and then the receiver on the other end of the part of the sensor. And so the less light that makes it to the receiver, that gives us an idea of how much turbidity is in the water. Okay, and then finally, the last variable we're going to look at today are nitrates. And so in water, nitrogen can be present in many forms and many molecules. So ammonia is an example. A nitrate itself is an example, nitrites. As aquatic plants and animals die, the bacteria break them down to form nitrates and nitrites and nitrates. So this is a natural process. However, we can artificially increase the levels of nitrates through fertilizer runoff from lawns and farming areas. The nitrate levels in fresh water are typically less than 1 milligram per liter, but man-made sources of nitrate, you can bump that up to above 4 milligrams per liter, and so that could be a problem also. All right, so let's get into the activity and check out the simulation. Okay, so I have the file Clean Water opened up in the TI-Nspire CX Premium software. You can use it in the computer software, or you can actually use this file in any of the science-inspired files in the TI-Nspire CX or CX2 graphing calculator. Either one's fine. All right, page 1.2, we talked a little bit about this already, about the different variables that can affect water quality. We're going to look at 5 variables, so DO, temp, pH, turbidity, and nitrates, but the reality is there are a bunch of other variables we could look at. We're just going to focus on those 5 today. And these variables can interact with the water in complex ways, so it's best to consider the variables as a group rather than an individual parameter. So we're going to look at sort of all of these together since they all affect one another. And so it's a little different than a typical lab where we're only looking at one variable at a time. We're going to compare samples of water based on the measurements of these 5 variables within each sample. Okay. All right. Next page. Question 1. There are many factors that affect water quality. When determining water quality, A, each factor is considered separately from the others. We just read that that's not the case. B, the factors can affect each other, so they are analyzed as a group. That's absolutely true. Or C, only 5 factors are used to analyze water quality, and that is definitely not what we said. We're only looking at 5 today, but in reality, there are many factors that you can take a look at, especially when we're talking about drinking water. You really want to make sure that the drinking water is clean if you're in charge of the drinking water for a municipality or a town or something like that. Okay, so we're going to look at aquatic ecosystem water samples today. And we're going to use a virtual lab using a data collection system. So we're going to use sensors basically for each sample of water. The way this is going to work, we're going to select the green record button on the virtual calculator screen to begin, and then we'll drag the probe into the beaker, get a measurement, wait for it to stabilize, and then we'll press the center click button to actually capture that data point. All right, so water sample 1, what you see here is TI-Nspire CX graphing calculator. I'm going to use that little green button to start collection when I'm ready, and then I'll use this little click button to capture the data point. And it's going to capture the data in this table down here, and then later on we're going to look at a graph. We're going to look at several graphs to figure out what's going on with that particular sample of water. Alright, so we're going to look at temp, pH, nitrates, dissolved oxygen, and turbidity, and 3 different water samples. Obviously we're going to start with water sample 1. So I'm going to grab the temperature sensor, go ahead and put that in the water. We're going to wait for that reading. Oh, actually we have to press start first. And we'll wait for this reading to stabilize. Looks pretty good, 31 degrees C. I'm going to collect that data point. Now we're going to jump over to pH. Put the probe in, boom, like that. Looks like pH stabilized at 8. Alright, and then nitrates. One milligram per liter, good. Dissolved oxygen, 2 milligrams per liter. And finally, turbidity. Remember, turbidity is basically how cloudy is the water. Looking at a reading of 10 NTUs. Alright, got that one too. Alright, so now I need to stop collecting, and I need to change my water sample to water sample 2. I'm going to put the temp probe in. I'm going to go ahead and press start. Alright, I got that point. pH. Eight. Nitrates. Pretty stable reading there, 10. Dissolved oxygen, 9 milligrams per liter. And then turbidity. Whoa, alright, wow. It's a pretty high reading. Alright, got that one too. Alright, let's go to water sample 3. Start collecting. 24 degrees C. pH. 8. So nitrates. 4 milligrams per liter. DO. 10 milligrams per liter. And turbidity, last one of the last sample. 26. Okay. Got that sample as well. Stop collecting data. And let's go take a look at the data, see what we gathered here. So water sample 1, water sample 2, water sample 3. And looks like we have higher temp for column B sample 1 compared to samples 2 and 3. pH is consistent between all 3. Nitrates went from 1 to 10 to 4. Dissolved oxygen is pretty low. It's 2 to 9 to 10. And turbidity was a little bit all over the place. The lowest turbidity was the first sample, highest was the second sample, and in the middle was the third sample. Alright, so data was captured on graphs as well as the table. This graph was temperature versus sample number. So sample number 1, the temperature we knew was 31. Sample 2 was 24. Sample 3 was 24. So sample 1 is higher in temp than 2 and 3, and that's going to become useful here in a little bit. Actually, what's going to happen is in a few minutes I'm going to tell you about each of the locations that the water was collected. And then from the data and from what you know about each location, you need to match the water sample with its location. Okay, so that's kind of what we're driving at here. Now it's going to be hard to do with pH because pH was the same for all 3 samples of water. So pH individually isn't going to help us much. Nitrate, however, we went from sample 1, I had a reading of 1, so pretty low nitrate levels. Sample 2 had higher nitrate levels at 10. Remember, nitrates can come from agricultural runoff, so like farms that use a lot of fertilizer. And then sample 3 had a level 4 of nitrates, so a little bit moderate there. But sample 2 had a lot of nitrate. That's going to be useful for us to try to match it back to the source of the water samples. Dissolved oxygen, sample 1 had a reading of 2, so it's relatively low. I would say this is probably not moving water, or it's very, very warm water. It's one or the other or both. Because remember, DO is negatively affected the warmer the water is. So the warmer the water is, the lower the DO. The colder the water is, the higher the DO. So that's something to keep in mind as well as you look at these much higher readings in samples 2 and 3. Turbidity, remember that's how cloudy the water might be. Sample 1 had relatively low turbidity, I mean 10, it's not bad. Sample 2, however, had high turbidity, so something was going on there. Could have been runoff from a heavy rain. There could be low vegetation potentially in the land around it, so the sand and the sediment are loose, and so they can leach into the surrounding water. And then sample 3 was, comparatively speaking, was kind of in the middle at 26 NTUs. Okay. All right, so let's see. Question 2, location A. So here's the idea. We have locations A, B, and C, and samples 1, 2, and 3. So we need to match the samples back to the location. And this tells us a little bit about each location. So location A, this sample was taken from a large, fast-moving river. The river's tributaries normally drain both urban and agricultural areas with buffer strips that slow runoff and decrease the amount of sediment entering the river. Which water sample is this? Is it 1, is it 2, or is it 3? And so that's the idea, is that we're going to try to figure out how to match these things up. So, okay, a large, fast-moving river. Large, fast-moving river. So I would say that it's probably going to have high dissolved oxygen, and the tributaries normally drain both urban and agricultural areas, but there are these buffer strips that are along the river to slow down the runoff. So even though you've got sort of a draining of these ag areas, looks like they have some measures in there to sort of mitigate that, to slow it down a little bit. So if we go back to our table, we have, let's see, we're looking at temp. I don't know if a large moving river is going to have very high temperature. I think it's going to be probably 2 or 3. Nitrates, said there was some runoff, so it could be 2 or 3 here. DO, remember large fast moving rivers are going to have higher dissolved oxygen, so it could be 9 or 10. And then the turbidity rather, because it's a river, there's runoff, you're going to get some turbidity. So I think we can rule out number 1. Okay, I don't know that we can tell if it's 2 or 3 yet. So we're gonna keep moving and try to figure out if we can narrow it down. Let's go to question 4. Location B. The sample was taken from a farm pond after a heavy rain. There is little vegetation on the banks surrounding this pond. The pond's located in the middle of a bean field that was recently fertilized. Which water sample is this? All right, well, let's go back to the data. So it's a farm pond, heavy rain just hit, it's not a lot of vegetation, so chances are there's probably some high runoff, high turbidity. And it looks like between the first one and the second one, a small pond with a lot of runoff. I'm thinking the farm pond might be this one here. Let's see. Now, the only thing though is a pond could also have low dissolved oxygen, but this one has, relatively high dissolved oxygen, but the turbidity is relatively low. Now nitrates, high nitrates, remember we said that it just got fertilized. Fertilizer is heavy in nitrates. I bet it's going to be number 2. Oops. Let me do that. Let me keep going. pH doesn't really help us here. Temperature is 24. It's between 2 or 3, but I'm leaning on number 2. I think it's probably 2. All right, but we'll keep moving here. All right, and let's see. Look at the last location, location C. This sample was taken from a shallow creek. Remember, shallow creeks are more susceptible to the sun heating it up, near an urban mall area. runoff from the parking lot drains directly into this creek. So if your car leaks oil or spilled a little bit of antifreeze, it's going to probably end up in the creek. Because the creek is shallow, it's very slow moving and the bottom is easy to see. There are a few trees along the banks of this creek. Which water sample is this? All right, so I think this is number one, just because we know that water sample one had very high temperature, and so shallow creek we know is more susceptible to that, and there's not a lot of vegetation given its shade. So I'm going to say this one's number one. I went through the reasons why. Now we have to kind of distill 2 and 3 down one more time to see which ones this is. So location A, I think, remember this is a large fast moving river. There's drainage, but they are buffering the drainage. So that means that not as much sediment's getting in there as could be. And remember the turbidity was kind of in the middle. Dissolved oxygen's the highest. You would expect out of these 3 bodies of water, you'd expect your DO to be highest in a large fast-moving river versus a pond and a creek. Nitrates were moderate. Not a lot of fertilization going on, unlike number 2. And temp didn't really help, pH didn't help distinguish. So it's got to be, I think, between the lower nitrates, but they're still elevated a little bit, just not as high as number 2. The high DO and the moderate turbidity, I think that water sample 3 belongs with location A. So we're going to say this is water sample 3, which means process of elimination, we can say that water sample 2 belongs with the farm pond. And that makes some sense just because of the seriously high turbidity. Remember, a rain just came. And the seriously high nitrate. Remember, they just fertilized the bean farm, so that's what's going on there. All right, so hopefully that made some sense, and you got something out of this. The 5 parameters we studied today are not the only 5 that are used for water quality, but these are good indicators for what's going on with the land around it. You can tell if there's vegetation or not, just based on the amount of turbidity and runoff. But this will give you a better idea of how we actually measure water quality and why these parameters are important, and ultimately why it's important for us to be careful with what we put in our yards and our gardens and things like that, because a lot of times that stuff ends up going, because of the watershed, they'll end up in the body of water nearest you. All right, with that, that's it for this activity, and please check out more video lessons at TI Calculators, all one word, on our YouTube channel, and look forward to doing another one of these with you real soon. Thanks. Bye-bye.